Hi. In this section, we're going to be looking at the various theorems that confirm if two triangles are going to be similar. Now, for this to work, we need to recall that similarity means that two figures are identical in shape, but not necessarily in size. Another definition we can use for similarity is to talk about how one is going to be a dilation of the other. So that if I were to take my two triangles, so there's one, oops, whoop, let's go back and redo that. Hit, edit, redo. There we go. I don't want to get rid of it. I want to copy it and paste it. There we go. Now let's make it larger. So now I have two similar triangles. And what we've talked about is the idea that if these are going to be similar, no matter how I orient them, that they're going to be dilations of each other, which means I can, for example, I can set them up and I can see that those are going to match. Everybody's running along the same lines. It seems to fit that format. Or another way to show that they're a dilation of each other is I can draw those dilation lines. And I can see that all three of those lines are going to converge. So we'll do that one. We'll do that one. And then we'll do this one. And you can see that they all meet at the same point. So they're obviously going to be dilations. That means that once I rotate them into place, they're going to be similar. Now our challenge that comes in is if I were to take that triangle and I were to make it bigger, what if I can't move it around the page? Or worse, what if it's been rotated as well as dilated? The figure is still similar. But now I need a strategy to help me establish that they're going to be similar. We have three theorems that will accomplish this for us. The first theorem is called the angle-angle theorem. And what this one says for similarity is that two angles are all I need. So if two pairs of angles are congruent, then the triangles are similar. So in other words, if I take my two triangles, so here's a triangle, and oh, it's a right triangle. That worked out nicely for us. Now I were to take another triangle, put it over here. Let's make it a dilation, and let's rotate it. There we go. Are they similar? For this theorem to apply, I would need to show that we have one pair of angles congruent. So that would imply that A and A prime are congruent. And I would need to show that a second angle is congruent. So angle B is congruent to angle B prime. If that's the case, then I can conclude these two triangles are going to be similar. That also means they're going to be proportional. It also means that all the ideas about similar figures can be mapped between them. I just need those two pairs of angles to be congruent, which makes some sense, because if two of the pairs of angles are congruent, the third has to be by the triangle sum theorem. Once I've got that, all my angles are congruent, and that sets up everything that follows with similarity. The second theorem that establishes that these are going to be similar is the side similarity. Now what this says similarity. Okay. This says that if I have all three pairs of sides are proportional, then I can conclude my triangles are going to be similar. So I'll write that down. So if two, no, I keep saying two because I'm thinking about angle, angle. So if three pairs of sides are proportional, then triangles are similar. Now, think about what we said about similar figures. We talked about that idea of proportionality, that there will be a common scale factor for the sides. What this does is it lets me work without having to deal with any kind of angle calculations. Simply by measuring lengths, I can establish similar figures. So let me do a diagram to show what we're talking about in this particular case. So if I were to say have something that looks like this, and then maybe I do that, boom. And let's say that this length over here is 10, this length is 8. Let's say this over here is going to be, let's get some better numbers. So let's say 12, 10. So that was, let's say this is going to be, I still like those numbers. You know what? Keep life simple, right? Never do an example with really hard fractions. Okay, so let's say this is 3, that's 12. This is 2, this is going to be 8. This is also 2, this is also 8. Now I can check to see, are they really proportional? So I can check. Well, let's see. 3 divided by 12 gives me a ratio of 1/4. Okay. 2 divided by 8 gives me a ratio of 1/4. 2 divided by 8 still gives me a ratio of 1/4. Since I keep getting that same fraction of 1/4 for each of these, I can conclude that I have 3 pairs of proportional sides. I know they're proportional because I keep getting the same scale factor. 3 is blown up to 4 or 12. 2 is blown up to 8. 2 is blown up to 8. So that's enough to tell me I'm looking at similar triangles. Also tells me that the corresponding angles are going to equal each other. So that also then goes on to tell me things about the angles out there at the corners. But for now, I have enough that I could write, I could say that triangle, that's going to come cut in with me. Let's put it over here. I could say that triangle ABC is similar to triangle EBD. I can identify these two triangles as similar based on this. The last thing we're going to look at is called side angle side similarity. So let's write that one down. So side angle side similarity. And again, we're trying to find ways to mathematically and geometrically prove two triangles are going to be similar without having to A, move a picture around to verify it's a dilation, or to have to do a lot of measuring of all the sides, all the angles in order to get to the definition. We're looking for a shortcut to prove similarity. So these are 3 of the shortcuts. We had the angle, angle, side, 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 and now we've got side, angle, side. So what this is telling me, as it implies, that as long as I have 2 sides and the angle between them, that's enough. Let me do another diagram like the one I just did. So here are 2 parallel lines, like that. There's that. There's that. Let's slap some numbers on there. So let's say this over here is 3, 2, and 4. Well, I don't know that guy. We'll leave him out. So 3 and 2, and let's say this length over here is going to be 15, and let's say that's 10. Now, from the diagram, just given that, this is an example of that side angle side. I have two sides and the angle between them. So for example, by vertical angles, I know this angle here is congruent to this angle. Vertical angles are congruent. So that then tells me, let's check our proportionality. 2 divided by, let's go 10 divided by 2 this time. 10 divided by 2 gives me 5. So that's the scale factor of that segment. That's taking this segment and this segment and checking for their scale factor. Now let's check the other one, 3 and 15. So 15 divided by 3 is 5 again. So that means these sides match up, and they both have a 5. So I can now apply the rule, which says that if two sides are proportional, meaning they have the same scale factor, and the angles between them are congruent. Close enough. Then the triangles are similar. Now what's going to do with that? Not D, triangles. There. Then the triangles are similar. So again, this is another illustration of that side angle side similarity. So we've got angle angle, side side side, and side angle side. We should probably start looking at some actual problems then that are going to use these. So hang on for those.